Okay, circuit recap. Just like I just said, I'm just going to go through this real quick. I'll just stop wherever I think we might need to emphasize anything. But basically know all the basic principles. So conservation of charge, um, Kirchhoff's current law. I'm not going to go through it. Just the basics of potential, what a potential is. Just see, a lot of times when I ask people, like, what's the voltage at this point, without giving a ground, they'll just answer, assuming something is ground. So that's the key thing you always have to remember in potential. It is always reference to something, right? So in physically, it's basically an electron where you're getting from some point in galaxy where there are no charge, right? And the work needed to get to a point, that's potential. But in a circuit, it's not like you have that point in the galaxy. It's always some reference point. So you need to know how to at least do a quick calculation. So, and basics of the electric field too, what electric field is, right? So the very basic definition, it's the force experienced by a charge at a certain point, right? And you take that and you plot it in an entire space, and that becomes the field basically, right? So, and once you have the field, you can put that charge and you should experience the same force because that's how you calculated it. So for an arbitrary system of charge, if you have it, you sum of all of them vectorally because it's a vector field, right? It's not a scalar field. Potential is a scalar field, but electric field is vector. So, and the potential, if you have electric field, you're going to get a potential between 2 points because that was the definition how you found the electric field. So it's actually the reverse. We always think it's the line integral of electric field, but that's how you actually calculated electric field, right? You actually brought potential from every point and you actually plotted the electric field. But when electric field is given to you in a certain space and you need to find the potential difference between 2 points, then it's a line integral between those 2 points, right? So, and if the field is homogeneous and it's in a straight line, then it's just the potential difference divided by the distance is your electric field, like in a capacitor, right? So a capacitor, it's typically, assumed as a homogeneous field inside the dielectric. So if you have to find the electric field inside like a two true parallel plate capacitor, then you just take the potential difference across it and divide it by the distance, and that's your electric field, right? So that's for a uniform field. And the corollary of this is if you take the line integral around a loop, obviously it's zero because you have come back to the same point. And that's your KVL, right? That's your Kirchhoff's voltage law, because here you're taking a line integral. In Kirchhoff's law, it's a discrete points because you're assuming between those two discrete points, it's a uniform field. Here it's assuming it's not a uniform field. Okay, and the KVL is, like I said, it's that this corollary here. So it's essentially the line integral around this field, which is in circuit terms, it's the voltage summation of the voltages of all the nodes, basically. Okay, and what do we use these laws for? And sometimes it's good to define it and know it, because a lot of times people will just know this discretely. And if I ask them, okay, what are you doing this for? And they say, I don't know. This was what was taught to me. I don't know what I do it for. But I think so. It's to analyze, understand, and design. But the most important part is for linear time invariant system, right? So you can't use this in any other system if it is not LTI. So it has to be a linear time invariant system. Then you can use all these principles. And honestly speaking, throughout your career, everything is a nonlinear system. Nothing is a LTI, right? Which means that, and all these simple problems will become so complex that you'll never find a solution to it. But that's where your engineering, sort of the art of engineering comes in. You convert all these nonlinear, because nothing is a linear system, right? Everything is actually a nonlinear system. But you actually convert all these linear systems and approximate them into LTI and solve them, because the tools does that. So you have very fancy and sophisticated tools to do that. But when you do hand calculation, you have to break it down to LTIs. It's only there are a few people in the world who can do, you know, nonlinear and time variant systems by hand, but most people will need basically tools to do it. Okay. Um, so few other, so that's the sort of the network theory part of it, like mostly kind of the physics part of it. The other few principles which really helpful, the superposition. Again, this is one principle I think, it should be in everyone's toolbox. Everyone knows it. Everyone is taught in there for, but nobody uses it, which is, kind of a, waste of a beautiful principle. um, Again, so I think everyone knows about this principle. So it's superposition is again only valid for LTI systems, right? So you have a linear system, and if you give excitation and you give output, and you give another excitation, you get an output. So the principle says that if you sum the input, then the output also will sum, right? So you don't have to, so you basically take arbitrary inputs, if you can break them into linear independent ones, which is called the basis form, basically, right? It's like the basis form. Then you can individually calculate them and then sum the output. Then it makes it much easier for you to solve a lot of complex system. Fourier is actually one example, right? I mean, if you take a system and once you know it's linear, then you find out the frequency response, then you know that for any arbitrary system, it will look that, because every arbitrary signal is a composition of sine waves, right? So, and if you know the sine wave um, independent response of each sine wave, and you know it's a linear system, then you know for every arbitrary signal, that will be the output, right? If it is not a linear system, then you can't assume that. So that's the superposition principle. But the other thing about the superposition principle is it's reciprocal, in the sense, if you know a system is linear and you want to find a response, you apply superposition. But if you don't know a system is linear or not, but you obviously have to know their transfer function in some way or the other, or you know their mathematical form, then you can use superposition to prove if it is a linear system or not. Classic one is a capacitor and inductor, right? So I tell everyone that till today, in my 4 years here, that's the first question I always ask undergraduate students: is capacitor and inductor is a linear? I still haven't gotten a right answer. They'll usually say nonlinear because that's their intuition, because they think linear means the VI should be a linear, right? But that's not the definition of linear system. The definition of the linear system is if superposition can be applied, then it is a linear system, right? So, so if you apply superposition to capacitors and inductors, they're valid. So they are linear systems, right? So that's why you can take a RLC circuit and that's a linear system. But if you add a diode, then it's not, right? Because diode, if you apply superposition, it's not valid. Okay, so remember that if it's a linear system, you can apply superposition to find the output of two independent inputs by doing their two independent, summing their two out, summing or taking difference, whatever it is at the input. And it's reciprocal either. If you want to find out if a system is linear or not, apply superposition as well. Okay. Time invariance, just a definition. You just need to know. You really don't use it in your day-to-day life of solving problems, but you basically need to know. And all it is just says that if you take a time domain response of a system and you take the input and you delay it or advance it or delay it by any time, then the response also gets delayed or advanced by the same time. That's, kind of the simplified form of what a time invariance means. And if it is not, obviously not. Circuit elements, I think I'm just going to I think everyone knows this. So the basic circuit elements which you're dealing in, plain circuits are basically the RLC and the two independent sources, the voltage sources and current sources. And the voltage sources, always remember, right? If it is ideal voltage source, sorry, then no matter what the current is flowing through it, the voltage across it is always fixed, right? And the current source is the opposite. Doesn't matter what voltage across the current source is. If it is ideal current source, then if it is minus 1 kV, plus kV, 3 kV, 1 volt, minus 3 volt, the current through it is always that I naught. Okay. And then other than that, you have 4 dependent sources as well. So, and it's 4 because you have input and output, and each of the input can have either a voltage or a current, and the output can be a voltage or a current. So you have basically 4 combinations, right? So the voltage control voltage source is if you the input voltage, whatever is the input voltage, then the output voltage some alpha times or gamma. Basically, it's a constant times output voltage. That's a voltage control voltage source. And when you're up, for example, modeling op amps, your first order modeling is this VCVS, because it's a, you can see it's a infinite input impedance. So there is no current flowing through it, but zero output impedance. That means you can apply any load and it will source or sink the current to keep the voltage alpha times V1, right? So that's a ideal dependent source. And then the voltage control current source is, input is a voltage, again infinite impedance, but the output is some G times um, the input voltage. So this is what's called a transconductance. So if you have a transconductant amplifier where you're converting from voltage to current, sorry, this is uh, yeah, transconductance, where you're taking, so basically a transistor is a, this is a model for a transistor, right? Your input is, this is your gate voltage and output is a current. In transistor, it's, you know, GM times or beta times or whatever it is. Here it is that G times. So if you're modeling a transistor, this is how you model. Okay. And this is the basis of an amplifier too. See, op amp is not an amplifier. Op amp is a result of an amplifier. But the basic element of an amplifier has to be a transconductance. Okay. And that's one key thing you have to remember. A lot of times people will ask you in interviews, like, what's an amplifier? For example, is a transformer amplifier? A 2:1, let's say. So if you make a transformer 2:1 winding, so you give an input voltage, the output voltage is twice that. Is it an amplifier? No. Why not? Why is it not?
Transconductance.
What's that?
Uh, No transconductance is taking place because we are applying voltage and getting voltage.
Yeah, but what has it to do with amplifier? So what's amplifier then? So Subham is saying there is no transconductance, that's why no amplifier. But why? I mean, is that the definition of amplifier?
No, sir.
So what's the definition?
Sir, it either increases my current or my voltage.
No. So amplifier is power amplifier. Okay. So in a transformer example I gave you, so for, let's take an example of a speaker, right? So let's say, for example, let's say you have, let me just draw this here. So let's say you have so speaker, I'll just I mean your cell phone, I'll model it as some voltage source, right? I'll take some impedance RS, and so let's say this voltage is some VI, right? And let's say I put a speaker whose impedance is usually what, 8 ohms or whatever it is, right? 8 ohms, let's say. So that's your RL. So let's say you want to generate 1 watt of power, right? So let's just make it simple. Just make it 1 ohm. Okay. So 1 ohm, 1 watt power means what should be the V peak? 1 volt, right? V square over R, right? So P out is equal to V square over R. So I need 1 volt peak. Let's say this was 100 millivolt. Okay. So you'll say, okay, I'll just put a transformer. So I'll take this, my cell phone. I know this is 100 millivolts, so I'll do a transformer 1:10, right? 1:10, and that's it. I'll get 1 volt here, and then I'll put the 8 ohms, and then I'll get 1 volt output. What's the problem for this? So you were seeing 8 ohms here. Sorry, 1 ohm, right? So we did 1 ohm, so it'll be 1 ohm here. So you're seeing 1 ohm load here, and you're saying I cannot drive 1 ohm load here. 1 ohm is only giving me 100 millivolts, right? So you did a transformer and you put 1 ohms there. Okay. So what happens? So this is 1:10 still. You'll still see the 1 ohm here, because what will happen is, to drive this, you have to drive 10 times more current here, because the impedance gets reflected by 1. So you'll see 0.1 ohms now. Because now when I see, so if you have a transformer 1:10, and I put a 1 ohm resistance here, when I look here, it's zero point 0.1 ohms. Because V times I, the power has to be conserved, right? It's a passive element, so the power has to be conserved. So whatever is the input power, so the output power has to be same. So basically you haven't done anything. So you try to increase the voltage, but you actually have to increase that current 10 times. So you basically boil down to that same part again. So you can't do amplification. So that's why you need a voltage control current source. So what that does is then you can supply some voltage and that the output is independent of the load, right? So the output will drive the load. So now if I have a transconductance here instead of a over here, over here, so I have a transconductance. So this is, let's say I'll draw the four port model here, and this is 1 ohms. So I want 1 volt here, right? 1 volt here. 1 volt times 1 ohm is what? I mean, 1 ohm by 1 volt is 1 amp. So I need to drive 1 amp here, right? So I just make sure that this transconductance gain times 100 millivolt is 1 amp here. Then I'll do power amplification, right? So that's the key for amplification, is that you need a transconductance with a very high transconductance value. So what it does, it actually does impedance transformation. And again, that's the key in amplifier, that you're actually transforming impedance. So you're taking a high input impedance and transforming into a low output impedance. Okay, so all your power amplifiers, for example, in your cell phones, you have power amplifiers. So when it's transmitting power, so the output impedance is 50 ohms, because it needs to transmit 2 to 3 watts of power, sometimes 5 watts of power. But your output voltage getting out from your amplifier is only few millivolts, 10 millivolts. You can't provide for 50 ohms that much, right? You need a huge voltage. So that's what the amplifier does. It does a impedance transformation. Okay. So, so that's, you can imagine VCVS as the ideal model for a, transconductance. And then you have the current control current source, where your input is a current. So that means your input impedance has to be 0 because you're sensing current, and your output current is some I times that, right? Current control, sorry, it's a current control voltage source. So it's some I times V. So this is what's called a transimpedance amplifier. So TIA, you must have heard. So it takes a current, converts into a voltage, like a lot of sensors. A lot of sensor outputs are currents, they're not voltage. So they're very tiny current. So you take a transimpedance amplifier, and a classic transimpedance amplifier in op amp is basically just this, right? So your sensor is just providing a current. So let's say this is I. So output is minus I times R, obviously. So you have to invert it, but essentially you get a voltage output. So that's the model for a transimpedance amplifier, ideal trans. And the last one is basically current controlled current source, where your input is a current, output is also a current. Okay, clear? All right. So network analysis. So, uh, using the KCL KVL, any linear network, you can basically find solutions for all node voltages and branch currents, right? And that'll give you two n independent equations, because you get n voltages and currents for your branches. And so that's like a brute force way of doing it, right? So you can do it. But I think all of you know that there's a much more efficient way of solving it, which is your node equations, okay? And the node equation is basically, it's a three-step process. You pick a reference node, and typically the reference node is, if you have one independent voltage source, take the negative part of that. Like, let's say you have a battery, take the negative part of the battery, because it's not like that is the only thing you can take. You can take any node as a reference. It's just that your calculations are tractable. Otherwise, you're dealing with like a lot of negative numbers, right? Instead of that, you deal with tractable numbers. So you choose a reference node, assign a voltage variable to the other nodes, except for independent voltage sources, because that because it's some V times, I mean, V plus the other node, right? So you don't have to write the reference. And then write the KCL for other nodes and solve it. So you should have n equations, n unknowns, and you solve it, right? And so let's take an example here. So if you have this as a V naught, which one would you take as a reference? This one, right? This would, I mean, like I said, you can take any of these as references, but obviously if you take this as a reference, everything will be minus V naught this, minus V naught that, and so on. Whereas this is a natural thing. And that's what I mean. Like when I usually give this circuit and ask somebody, what's the voltage at this point? And if I haven't shown this, obviously everyone assumes this is the ground, but you should not. The first question you should ask is, which reference to which node, right? So if I have specifically drawn this ground, then obviously I'm saying with reference to this node. But if I've just drawn this circuit and I'm asking you what's the voltage at this point, then you should ask me with reference to what node, right? So in the node equation, so you made this ground. So there are 4 nodes here. You make this ground. This obviously you don't have to because this is always V naught, right? Because this is ideal voltage source. And then you name this, let's say V1, V2. So you write the KCL at this point. So that's your first KCL. So this will be what? V naught minus V1 by R is equal to I naught, right? And the second one will be the KCL for this node, which is I naught equals to V2 over R1. So this is R naught, right? And then you solve these two, you should get, and obviously this is a simple circuit, so you can see V1 should be equal to V naught minus I naught R naught, right? And V2 should be equal to I naught times R1. That should be, if you solve these two, you should get this answer basically, right? So that's if you did the just the KCL KVL way, then because there are 4 nodes, you're going to get 4 branches, 4 nodes, 8 equations, 8 unknowns, you solve it. But here you have just 2, right? So that's the beauty about this node equations. And same thing again, if you did this again, take the reference node. This is obviously always 10 volts. You don't have to do this. And then you just have one node, right? Because this is already ground. And you just apply KCL for this node, which will be uh, 10 minus V1 equals to zero point 0.2 milliamps uh, plus V1 over R2, right? That's your KCL, and V1 is the only unknown. Solve it, and you should get V1. You can also solve this by superposition, right? Because there are 2 independent sources, right? The first independent source is 10 volts. So when you do superposition, you basically zero out all other independent sources. So if you're zeroing this out, then V1, let's say we'll call it dash, is equal to what? 10, 10K, 10K. So this is 5 volt, right? That's your first solution. And then the second one is
5
this,
millivolt,
was that?
5 milli.
No, it can't be 5 milli, it's a volt, right?
Sir, 10
So
kilo ohm.
Voltage divider, yes, 5 volt.
come on, Subham, you can't mess up units. It has to be voltage. You said milliohms and then you said milliamp. You basically did the 2
Sir,
others which are not.
millivolts, millivolts.
Okay, so you said milli. Okay, that's also wrong, right? It can be millivolts. So, so in the second one, you short this, right? You short this, and what is the parallel resistance?
Point 1 will be in both the branches. Current division.
Yeah, current division, or better way is you have what? 10K. And these are the things you have to, if you do a lot of them, it'll become, your life will become easier. You do that, it's just 5K, right? It's 5K, 0.1, and it's 0.1 flowing in this direction, which means this is positive, this is negative, which means 5K times zero point 0.2 is how much? 1 volt,
So
right?
1 volt.
Minus 1 volt, right? And then obviously V1 is you add V1 dash, so that's superposition, right? That's 5 minus 1 volt, that's 4 volts. Okay, Subham, you agree with this or you still want to have 0.2
Yes, sir. Yes,
millivolts?
sir.
Okay, so don't jump into the answer, okay? See, this is where I say sanity check, right? You always have to do sanity checks to make sure your answer is right. So when you got 5 volt in one, and you're saying you got 0.2 millivolts in one, that means either your current is in milliamps, resistances are in ohms, or your current is in amps, resistance is in milliohms, right? If either one of them is not right, that means you have made a mistake. So you should go back and check before you say milliamp. Okay, so I always keep saying for engineer, uh, the bane of existence is sanity checks, right? Approximation and sanity checks. You don't do sanity checks, you're going to do, you'll be spending a lot of time actually going through mistakes for sometimes months and before you realize it'll be going, right? Like for example, you remember I gave you this problem when we had a 8-inch wafer and I told you it's a 1 millimeter by 1 millimeter. So I got an answer of 200. I got, I think, 20,000 and 60,000, right? So those ones you should just quickly look at it and say, okay, which one is the correct one? Because you go 1 milli, 200 squares, 1 milli, 200 squares here, roughly 40,000 if it was a square, because it's a circle, roughly 3 times 3 over, I mean, 3 over 4. So 75% of it, and you say, okay, 20,000 kind of makes sense, right? You don't have to have the exact answer, but at least you can pick saying that is close to work, right? So sanity check is your bane of existence. So I have a funny story I have to tell you about sanity check. When I was in my undergrad, I had a friend. We used to call him Superman because of this story. So when he was 8 years old, he's a brilliant guy, right? He's a professor in UNC Charlotte now. He's a brilliant guy. He said, when I was 8 years old, I was always worried about that. Why am I so unhappy? Okay, I need to find a theory where I can always be happy. So he said, I need a logical theory. So he said, okay, I found out this logical superstructure where the axiom is happiness. And based on that, I made the entire theory where I can lead the life. But he said my mother didn't fit in it. so, so, so he went and told his mother, and obviously his mother was all upset, and his father came and started banging him. I said, when your mother didn't fit, didn't you know your theory was wrong? He said, yeah, it didn't appear to me. So that's a sanity check, right? So we still laugh at that. And I really crack up. So anyway, so that's the sanity check you have to do. If your mother is not fitting, that theory is wrong, right? so so same way, if you're getting zero point 0.2 milliamp and you have zero point 0.2 milliamps, but 10K ohms, so kilo times milli is they cancel, right? Pico times giga, they will cancel. Nano times, I mean, nano times giga will cancel. So these are the things you need to have a thumb of rule always, right? You should always say like 1K times 1 pico is 1 nanosecond, because, minus 12 plus 3 is minus 9. So things like that. So these are the, because, these are simpler circuits. In real life, they're going to be much complex. If you don't do this, then you're just going to go crazy, right? The things will become very complex. Okay. So you can, yeah, just use network theory or this thing. Okay. So this is another example just showing you how the node analysis helps you a lot. Okay. Like you look at the network which is given on the left, you write KCL, KVL, you end up with 12 equations, 12 unknowns, solve it. Like I said, yuck. But if you apply the node equations, like for example, you start, right, you basically have a reference node, and this is obviously V naught. So you just have two nodes. You write the KCL for those two nodes and you solve it and you get the same answer, right? So two unknowns, two equation is much better than um, 12 unknowns and 12 equations. Okay. All right. So the last two thing I wanted to cover on the network is the Thevenins and Norton. I think everyone knows this. So I'll just quickly. So basically, if you have arbitrary, again, linear time invariant network, right? It cannot be a nonlinear network. Then that network, if you like, for example, you have another circuit or you have a test bench or if you have a load, the best way to check that, if you can, a lot of times you cannot make a Thevenin's equivalent, is you make a Thevenin's equivalent where you find, and the Thevenin's equivalent is this circuit here, right? Which is a voltage source in series with a resistance, and that voltage source is the open circuit voltage source. So if you open these two nodes and if you just measure with the voltmeter, high impedance voltmeter, whatever is the voltage, that is your VTH, right? And then the RTH is you make all the independent sources in that network zero. So voltage source is zero, current source is open. I mean, voltage source is short, current source is open, because these are independent sources zero. And then measure the resistance, and that becomes your RTH, right? So that's a Thevenin equivalent. And then the parallel or the reciprocal of it is the Norton, where your model is a current source with a parallel resistor, right? And excuse me, the current source is you basically, obviously disconnect any load, you short the output and you measure the current, and whatever you measure, that becomes your ITH. And then the RTH is same as before. So if you've already calculated the RTH using Thevenin, you just plug that in. Okay. So obviously they're equivalent. Then the question is, why do you prefer one compared to the other? It depends on the application. Okay, so for example, if you're doing a voltage amplifier, right? So you have your cell phone and you're driving another input of an amplifier to amplify it, then you would like to make a Thevenin equivalent of your cell phone because your the input impedance for the driver is open. So then if you make it, then your calculation becomes easier. You can do a Thevenins too, it'll work. It's just that your calculations become easier if you have Thevenin. Whereas, like, I gave you the sensor example where you're doing a TIA, right? So you have let's say you have a sensor network which is providing you the current and you're doing a transimpedance amplified to generate a voltage out, right? So here it's better you convert this into a Norton, right? If you do that, because it's ideally a current source, you find out the output impedance, and then because this is a TIA, then all you do is I times R naught. If you did a Thevenin's one, then you have to do a voltage transfer function, divide by the voltage, find the current, so on. Here, because you know the ITH already, so ITH times this R feedback gives you the voltage output directly. So depending on the application, they're used accordingly. Okay, so find Norton, I think this is uh, again, so find the open circuit voltage. Again, you can use superposition here. So this will, if you apply superposition, it'll be what? V naught minus I naught times R1 parallel R1 plus R, I guess. R1 plus R naught, right? So that'll be your VTH, and RTH is what? Just because then you
Not plus
open
R.
this, close this, so that's R1 plus R naught, right? So, so that's a Norton, and you can equally find out the Thevenins. Okay, so can you find out, so if I tell you to find out the Thevenin for these, so let's say these are the two nodes, can you find out the Thevenins or Norton for this?
No, sir. We have to
No.
remove the diode.
Yeah, the diode is there, right? There's a nonlinear diode here, so you cannot use that. But what you can do is you can find the Thevenin left of this, right? Because if you do, still it actually helps you a lot because then you're required. So typically this will be just to find out the current through the diode, right? So let's say you're doing a LED driver, you have the circuit the left, you're just trying to figure out how much current is going into the LED, the diode. Then if I take this, I can't apply any of the KCL, KVL, or any of the linear network theory. Uh, so what you do is you do the left of it, and then because you know this is approximately zero point 0.5, so you, and let's say this was VTH, this was RTH, and then you know that the current flowing through the diode is equal to VTH minus zero point 0.5 by RTH, right? So just by kind of moving the circuit left of it and finding wherever you can find the linear, you could find a very approximate, but this is actually very close. If the current is low and you know that the diode is close to zero point 0.5, then especially if this resistance is high, then and this voltage is much higher than zero point 0.5, then this equation will be very accurate actually, and most of the time it is. Okay, so sometimes when you have nonlinear elements, you can do tricks like this to do it. Or if you know that that nonlinear element is actually linear for that very small amount of voltages which I'm calculating, then what you can do is you can do linearization. And that's what we're going to talk in the first analog class in next week is and that will be the only thing which is missing from your sort of your device physics part is the small signal model, which in digital you'll never use, so that's why we never covered it. But in analog it's like that's like KCL, KVL in analog, so you need to know. Okay, so that will be basically telling you for very small signals, very small inputs or small variations, you can actually take a nonlinear element and linearize it. Okay, so like kind of what we did here. So we'll cover that next week. Okay, dynamic circuits. Okay, Chandan, see your question. I don't know if it's a question or a statement. VCVS is analogous to op amp. See, it's not analogous to op amp. What I mean is you can model an ideal op amp with VCVS, where the input impedance is infinite, and output impedance is 0, and the gain, the voltage gain from the input output is high. You can make it infinite or high. So you can model it. So a lot of times when you're modeling, like you guys, when you start modeling the SAR or the delta sigma, you'll see for the op amp initially, you might just use a VCVS to do it. And then if you want to add more more second order effects, like you know that the input impedance is not infinite. So you actually add a resistance, whatever your input impedance is. So let's say your input impedance is, 100 kilo ohms, then apply 100 kilo ohms. Okay. And your output impedance is not 0, it's 10 ohms. So apply, just put a 10 ohm series, right? And then your frequency response is infinite from 0 hertz to, you know, terahertz or whatever, the gain is flat for that, right? But in reality, you're going to fall off after some time. So you can apply a RC filter at the output to model that. Okay, so you can just keep modeling that. Okay, so dynamic circuits, again, just I think the theory part, you guys can go through it. I'll just maybe highlight some of the, um, yeah, so in any dynamic circuit, and again, linear dynamic circuit, it's composed of what's called a homogeneous and a particular solution. And you imagine the homogeneous solution as the solution for that circuit without any independent sources, right? And that's actually defines your circuit. So your poles of your systems, are basically your homogeneous solution. So when you say I have the poles of these circuits together, those are actually your homogeneous. Like your delay of your circuit, your RC time constant, those are homogeneous solutions. So if you take a RC circuit and you say tau equals to RC, that's actually your homogeneous solution. Okay. The particular solution is the solution given those independent sources. So if you have a voltage input or a current input, step input, or whatever input you have, and the response to that is your homogeneous. So in control system language, the zeros actually are your particular solutions. So for example, your zeros will change if I have one network and I change the input voltage source to a current source, it still is RC. Okay, time constant doesn't change, but my output voltage step will change now. And that, if you talk in control system or signal theory language, that your zero is changing, but your pole tau is still 1 over SRC. Okay, so always remember that. So in a network, if you're not changing connections, your poles never change, your particular solution never change. You can take voltage sources and move it around, but your time constant of the system will never change, or your poles of your system will never change. Only the zeros will change. Okay, and the zeros basically tells you what's the final value of your step function or whatever you're doing. Okay, but the time it takes is all decided by the network. So if you're not changing the RC values or changing the connections around, those things remain as it is. Okay, like for example, instead of a current source here, I put a series voltage source here, the time constant is still RC. Okay, so that's the key thing in this discharging. So I've shown here like one charging. I don't think, I think this is pretty clear, right? Everyone clear about the RC, or any questions? Maybe we'll do a, and this is, I've shown you the discharging one where, you don't have this one minus term here. So because your initial value is actually VC of 0. Some important properties, yeah. So if you have a discharging current like this, and if you find the slope at the time t equals to 0, that slope actually is your tau, gives you the tau. VC over 0 of tau gives you that slope. So if you don't know the tau of a system and you did a step response and you look at the discharging slope at the time time t equals to 0, and you extend it, so where it intercepts, that's your tau basically. Okay, so that's one way to find out. So experimentally, when people are trying to find out, so let's say you have many poles in the system, but a lot of times you'll see that there is always a dominant pole, right? So instead of trying to do that, let's say you did a step function, you said, yeah, I know there's a lot of poles around, but I know there's one dominant pole, and you want to know what the time constant of that dominant pole is. If you do this in experiment, you'll get your dominant pole. Okay. Um, these are, I'm just showing some typical values. So if you're discharging, then at tau, it's 37% of your initial value, which is basically you're starting at V. If it is a step response from 0 to VDD, then you are 63% because it's 1 minus that, right? So these are some of the good numbers to remember. Rise fall time, if you did use this equation, and again, most of the interviews or in real life when you're doing, you're always approximating to a single RC. So knowing these numbers a lot of times help you. So somebody tells you, okay, um, the rise time is 20 nanosecond. What do you think the RC is? Then you know the rise time they're talking about is 10 to 20, 90%. Sometimes they might define it as 20 to 80, right? You've seen those .lib files where they say 20 to 80. So you have to be careful. So maybe you should do a calculation for 20 to 82 and have that in your toolbox. So if you did a 10 to 90 and it's a single RC, then typically that's roughly around 2.2 times tau, right? So if you have a RC of 1 nanosecond and somebody asks you what's the rise time, then you say it's roughly 2.2 nanosecond from 10 to 90%. So these are good numbers to remember. The 5 tau number is a good one to remember, specifically for analog, especially when you're doing ADC, because you never settle, right? Theoretically, you never settle. You just get closer to the settled value because it goes till infinite, right? But if you plug in 5 tau, you're close to 99.4%. So for most application, we'll consider that as a final value. So that's why a lot of times you'll see that, oh, if my RC is 1 nanosecond, then the clock period I can operate is 10 nanosecond. That's because they say, okay, I need to settle for at least 5 nanosecond. I need to settle for the discharging 5 nanosecond. So the total clock period can be 10 nanosecond in analog sense. Okay. In digital, you don't do that, right? You say, after I rise to 90%, I can start discharging. So there you say 2.2 tau is good enough for me. So there you go. Instead of 10 tau, you say 4.5 tau, right? Is good enough. But like in analog, 5 tau, you see 99.4%, right? But if you are doing a 16-bit ADC or a 18-bit, you want to settle even closer. You want to get to 0.01%. Otherwise, you're not going to settle to a value you're trying to. So it's, but these numbers are good for most cases, not all cases. Okay, rise time, fall time by inspection. How do you think you can do it by inspection? What would you use? So let's say I have this circuit and I give a step response on both sides. I start I0 and V0 at 0 and step them to 5 volt and 1 milliamp. What do you think the output will be? And how much time it will take to reach, let's say, rise time? How much time? How will you calculate this?
The C value is 1 picofarad and equivalent resistance will be 2 kilo ohms. So we'll just multiply.
Why 2 kilo ohms?
We will look from the capacitor terminal, open circuit the cap, and we'll look from the
But why do you do that? Why are you doing that? So Chandan
that's
is
the net
saying that
output
he'll,
impedance
he'll
of the circuit which is being off.
yeah, so he's saying that you open the cap and look at the output impedance, but one way to look at it is you basically are trying to find out the Thevenins, right? Because this is the circuit you have calculated the RC time constant for, right? So VTH, RTH, right? And the RTH will be 2K. So it's 2K times 1 pico. So what's tau? 2 nanoseconds, right? Pico times K, minus 12 plus 3, right? Minus 9, so nanosecond. So K times pico is always nanosecond. So in IC design, you're either dealing with pico or femto. So and usually they're in the kilo ohms, right? So that's a good number to remember. So if you have a K resistance, a picofarad, so they're always in nano. If it is femto, then it is in picoseconds, right? So if it was a 2K resistance and 1 femto cap, then that would be 2 femtoseconds, right? Sorry, 2 picoseconds. 2 nanosecond. Okay, so then the rise time will be, TR will be 4.4
nanosecond.
nanosecond, right? And what will be the final value? Hmm? Final value of the voltage here, VC, sorry, VC final value. So
9.4.
VC infinity. What's that? So in this circuit, like in
0.194
the
times VTH.
Thevenin equivalent term, what is it? VTH, right? And what's VTH? So see, again, by inspection, you can quickly see, right? If you're doing superposition, this circuit is not there, right? So you just see 5 volts. And then when this is shorted, obviously there's no current being drawn from here. So it is minus 1 volt, because 1 milliamp times 1K is minus 1 volt, right? 1 volt. So that's 4 volts, right? So basically your step input will look like this, right? So when you step input both the 5 volt and 1 milliamp, it'll kind of look like that. And this will be final will be 4 volts. And this rise time from 10 to 90, let's say this was 10 to 90, this will be 4.4 nanosecond. Okay. By the way, 4.4 nanosecond is from here to here, not 0 to this thing, right? 10 to 90%, exactly. Okay, clear, everyone? And by the way, delay is usually tau. Okay, so if you give an input, and basically this is your step input, and the delay is 50% to 50%, so this is typically tau. Okay, so these are the numbers good to remember. That's it for the circuit. So what I'll do is let me stop this recording, and then we'll start another one.